Hi, welcome to Module 3 of Lecture 7. In this module, we're going to cover some notation, rules, and properties of classical definitions of probability. These will be generally useful beyond classical probabilities, but this is the context in which we're going to learn them. Okay. So let's begin with some basics. I already said before that this terminology meant the probability that some event A occurs. You often will sometimes see this used. They mean the same thing. In the book, we try to use the first one, but occasionally use the second one. It's good practice to see different notations. This means the probability that event A occurs. A probability is always between 0 and 1. If the probability is 0, that means it never occurs. I should note here, this is not sort of conventional, there's no chance of that happening. If the probability is actually 0, there's actually no chance of it happening. It cannot happen. Process is completely deterministic and the event never ever happens. In contrast, if the probability, of the event A is equal to 1, it always happens. Again, this is a deterministic process then, it always occurs. Event A cannot not occur, it always occurs. These are the extremes. In between we have normal stochastic behavior, random behavior, with the probabilities between 0 and 1. Okay, so we put it together and say the probability of A is contained in the set, is somewhere in the set 0 and 1. Right. It's an element of the set between 0 and 1. Okay. We call it a sample space with a set of all possible things that could happen. Therefore, the probability that the sample space happens as an event, if the event is something in the sample space happens, calling the sample space S, this probability is 1. This statement means something must happen. It cannot be the case that a random process produces nothing happening unless nothing happening is actually an event, right? When we say nothing can't happen, I mean that every single possible thing that could happen must be included in the sample space, including potentially the outcome that nothing happens. And that's a little confusing, but what I mean is, the latter meaning of nothing is the colloquial meaning of nothing. Oh, nothing happened. Right? In probability, nothing happening is an outcome. Right? For instance, let's consider a very definite dichotomous outcome. Either A happens or A doesn't happen. Right? We say A is the event A happening, and not A, that tilde means not A is the event that A doesn't happen. Well, one of A or not A must happen, right? It cannot be the case that both A and not A don't happen in classical probability. Okay? One or the other must happen. Therefore, if you list all possible things that could happen, including not an event, right, A or not A, if you list them all and include them in your sample space, then the chance that something in your sample space happens is equal to 1. Similarly, if we add up all the stuff, well, we'll get to that. We'll get to that in a second. So for single probabilities, we can deal with that. We might also be considering some kind of joint probability. A joint probability is a probability that two or more things happen together in some fashion. There are really two kinds of joint probabilities we might be interested in. The first is the probability that two events happen together. This is an intersection. You may also see this as with an upside down caret, with a caret. This means the probability that A and B occur together. This is a joint probability in which both events must happen for the probability. The probability specifies the chance that both events occur. If only one occurs, that's not here. This tells you the chance that both occur. This is a joint probability because it specifies the joint probability that two events occur together. The other kind of joint probability you might be interested in is the probability that one or the other event occurs. This is used with the union. Or the other one, this is or. These things mean or. The probability that A or B occurs. Sometimes we're interested in ands, sometimes in ors, sometimes in just plain probabilities, right? This is just a single probability. So these are kind of things you'll see. The top two lines represent joint probabilities. The bottom one is not joint, it's a single probability. Before we get into dealing with how to deal with joint probabilities, the last kind of thing we should talk about is what's called a conditional probability. This is read the same way set notation is read. This is the probability of A given B. The probability of A conditional on B. That's a really important concept, so it's important to get that clear in your minds. What that given or conditional means is that this thing specifies the probability that A occurs given that B has already occurred. Right? For instance, let's go back to that lottery example we did in the first module. Right? You might say the probability of winning the lottery was 0.00001, right? But really what you're saying is the probability of winning the lottery conditional on buying a ticket is 0.00001. If you don't buy a ticket, you cannot win the lottery. Therefore, the probability of winning the lottery conditional on not buying a ticket is 0. Right? So let's write that out, just to be clear. The probability of winning the lottery conditional on buying a ticket equals some small number. The dots just mean small. The probability of winning the lottery conditional on not buying a ticket is actually flatly 0. You cannot win the lottery if you don't buy a ticket, ignoring family members or whatever giving you free money. But, right, fundamentally, that's two different conditional probabilities, and we're referring to the first conditional probability when we discuss the chance of winning the lottery. Why is that important? Well, in understanding human behavior, you not only need to understand the chance of winning the lottery, you need to understand the chance of playing the lottery in the first place. So these things go together. And the conditional probability specifies only part of the story, but it's an important part of the story. The conditional probability is also central for Bayesian statistics because there you're trying to understand your beliefs given the data, right? Also true for likelihood, for maximum likelihood approaches. You're trying to understand your beliefs about coefficients, in this case not beliefs, but actual chance that they happen, or certainty about them, given data, given observations. The B here is the observations, the A is your posterior beliefs or certainty about coefficients, or at least the certainty about coefficients. I'm being very loose here. You get all this stuff in stats. The important concept is to note that conditional probability helps you specify updating from a prior belief to a posterior belief, or from, given some level of data. And again, ignore the stats terminology here. This is not meant to be a stats course. I'm just trying to give you a flavor for why you want to learn this stuff and why conditional probability is so important. It also will turn out a lot when you're trying to update your beliefs in game theory. You get new information about the state of the world or someone's type. That new information is B, and your beliefs given that new information is the probability of A given B, a conditional probability. So these are the core sort of expressions you're going to deal with. That covers most of notation. Now we want to go to actually figuring out how to deal with this stuff and learn a few more definitions that are important substantively and theoretically. Okay, we're going to start off looking at joint probability corresponding to AND. I'm going to use this notation, although you can't really tell from my writing if that's actually a caret or a U, upside down U, so whatever. Okay, both of them work just fine. Okay, so this is the probability that A and B occurred together. How do we actually go about dealing with this? Well, it turns out this is very closely related to the concept of conditional probability, so we'll do both at the same time. This can be written in two ways. Let's say you have two things occurring together. What we need to understand how to deal with that is whether or not they're dependent on each other or whether or not they're independent. If they're independent, then it doesn't matter, in some senses, what happens first or second, and the existence of one outcome, one event, has no effect at all on the existence of the other outcome or event, and the occurrence of the other outcome or event. They're independent. Independent in probability means the exact same thing it means in English, just that there is no relationship between two things. The chance that A happens has no effect at all on the chance that B happens. whether or not A happened previously has no effect on whether or not B will happen. If I roll one die, the number that pops up has no effect at all on what I roll on the second die. They're independent events. If they're not independent, though, then the chance that one happens depends on whether or not the other one happened. Right? They're correlated, they're connected. One is conditional on the other. The general example, the general sort of form of this is when we assume A and B are conditional on each other, and we can write the probability of two things happening together, A and B happening, in two ways in general. The first treats B having happened first as having happened first, and looks like this. Why is it like this? Well, let's consider that A and B happen together. Let's say B happens first. Well, the chance that B happens is just the chance that B happens, right? Nothing else happened already, so nothing can be conditional. B happened first. So the probability that B happens is the probability that B happens. We call this, for that reason, an unconditional probability. Here the probability of B is unconditional. It's either unrelated to A, or we've already averaged out what A can happen. That averaging out means we also sometimes call probability of B the marginal probability of B. This will become clear a little bit when we do distributions in the next couple lectures. Well, once B has happened, A being not independent of B, right, the probability that A happens is the conditional probability that A happens given B already happened. Therefore, if you want to know how A and B can happen together, one way of writing that is the probability that A happens given B happened times the probability that B happened as well. If B happens, right, that's this probability. The chance that A happens given that is this one. So if both A and B happen, that's this one, and it's equal to the chance that B happens and the chance that A happens given B already happened. So this is one way of writing an AND. A second way of writing an AND switches A and B. This means the exact same thing, but if A happened first, for instance, then first we consider whether or not A happened, and then look at the chance that B happened given that A already happened. So these are two ways, equivalent ways of writing the probability that A and B happen together. Which one you use, in some cases, depends on if things actually do happen first or not. If things don't really happen first, then it doesn't matter which one you use, and we'll deal with that explicitly when we deal with Bayes' rule in a later module. But this is AND. Now, what about if we actually do have independence? If A and B are actually independent of each other, then the probability that A happens given B is just the probability that A happens. If B's presence has no effect on the chance that A happens because they're independent, then the probability that A happens given B is the exact same as the probability that A happens by itself, the unconditional probability of A. Similarly, the probability that B happens given A, if they're independent, is the probability that B happens. And both of these are true if A and B are independent events. Okay. Well, what happens then? If they're independent, then these things reduce to the probability of A times the probability of B, which of course equals the probability of B times the probability of A, because these are just numbers, and numbers are commutative. Right. So if the two events are independent, then you get the chance that both of them happen together is the chance that the first one happens times the chance that the second one happens. This is why, for instance, the total number of things that can happen on two dice is 36. The chance of getting a 2 on two dice requires you to get a 1 and a 1 is 1 over 36. The chance of getting a 1 on the first dice by itself is 1/6. The chance of getting a 1 on the second die by itself is 1/6. Multiply them together, you get 1/6 squared is 1/36, which is the same as we would have gotten by going back to the original classical probability definition and treating all events as just compound events and not splitting them up into A and B. Right? So this way of doing it, looking at A and B, having A and B be simple events in this case, gives you the exact same outcome that you could get by treating the compound events by themselves and using the rules of classical probability. In both cases, you would get a 1/36th chance of rolling a 2 on 2 dice. So this is how you deal with ands and how you deal with conditional probabilities. And that takes care of one of these. Now, if two events are mutually exclusive, then this is 0. If events cannot happen together, then the probability that A and B happen is 0. So for mutually exclusive events, the probability that they both happen is 0. So this thing is mutually exclusive. Events that are mutually exclusive cannot both happen at the same time. Therefore, the chance they both happen, the and, is 0. We can understand that more clearly by going back to the conditional probabilities. Up here, now highlighted in blue. Well, if they're mutually exclusive, then conditional on B happening, A can never happen. That's what it means to be mutually exclusive. If B has happened, A cannot happen anymore. So that conditional probability is 0. Similarly, if A has already happened, then B can never happen. So that conditional probability must be 0 for mutually exclusive events. So now we can understand two sort of common usage concepts in terms of our notation, our formalism of probability. Independence means the conditional probability equals the unconditional probability. So the probability of A given B is the exact same as the probability of A for independent events. For mutually exclusive events, the probability of A given B is 0. A cannot happen if B has happened. So they are actually connected strongly. They're not independent. They're strongly dependent. In fact, they're so strongly dependent that one cannot happen if the other one has happened. They can't occur together. So that's 2 out of 3 of the sort of core things you're going to look at. Now, mutually exclusive definitions. Before we get to the third, though, let's deal with OR. Recall that this was the definition, or the notation for OR. That's actually a little more like a caret, a U than a caret, but still, caret works fine too. We'll upside down caret. So this definition, probability of A or B happening. Now, to get a handle on what this means substantively, helps to go back to sort of the Venn diagram concept you might have seen way back when high school or earlier. Assume you have a dartboard right here. This whole rectangle is a dartboard. And in a dartboard, you have two regions. There's a red region A, and there's a blue region B. Okay. When you throw a dart, you might land outside the region, or you might land inside the region. And we want to know what the chance of landing inside A or B is. So somewhere in that region. Well, what's that chance? Let's work through it intuitively. 1, we could land in A. That's this red region over here, right on the left. Well, so let's start with that probability. That's the probability of landing in A. Okay. We could also land in B. So there's probability of landing in B. Now, are we there yet? Almost. However, note that A is this entire region over here, including this shaded region in green. I apologize for people who are red green colorblind. But hopefully you can tell the shaded region, the rest of it. When you have probability of A, you include the chance of landing in that green region, in that middle shaded region. However, when you add B, you also include the chance of landing in that shaded region. So effectively, you're double counting the chance of landing in the shaded region. So you have to subtract one of those double countings. What is that chance? It's the chance of landing in both A and B. So we have to subtract one of those. We have to subtract this right here. So the probability of A or B happening is the probability that A and B happens minus the probability that, sorry, let me say, I said and instead of plus. The probability that A or B happens is the probability that A happens plus the probability that B happens minus the probability that A and B happen to avoid the double counting. Now we see a mutually exclusive comes in. if A and B are mutually exclusive, then if we were to draw the same kind of thing, I'll skip the colors, there's no overlap. We can just add the probabilities separately without this term over here. If two things are mutually exclusive, probability of A and B happening is 0, so that term goes away. So when you have mutually exclusive events, then this thing is going to equal probability of A plus the probability of B. Okay. So that's for mutually exclusive events. This was all done for 2 things, but again, all this works just fine for more than 2. Let's start with independent events. If you have independent events, say indexed by j, so you have a set of A sub j, each event of which is independent of all the other ones. Then the probability that they all simultaneously happen is going to be equal to the product of the probabilities that each individual one happens. So there's an exact analogy, and there's a j here, it's product over j. So there's an exact analogy between independence for 2 things, independence for as many things as you want. Similarly, if you have mutually exclusive events, A sub j, then the probability that they all happen at the same time, the probability that at least one of them happens, that A1 or A2 or A3 happens, equals the sum of all the probabilities of the individual things happening. So you just have to add probability of A1 plus probability of A2 and so on. You can ignore all the ands because they're mutually exclusive. Okay, so we're almost done now. This takes care of most of the things. I mentioned, though, there's one more definition we want to talk about, which is collectively exhaustive. So it's collectively exhaustive. A collectively exhaustive set of events, A sub indexed by j, effectively covers the entire sample space. If you add them all together, the chance that one of those events happens is 1. So if we add, if we have the union, the probability that A1 or, probability that A1 or A2 or A3, that happens, is going to equal 1. If events are collectively exhaustive, the chance that at least one of them happens is exactly equal to 1. They cover the entire sample space. This is very closely related to the fact that the probability the sample space occurs is 1. If events are collectively exhaustive, then they are the entire sample space. They exhaust the sample space collectively. And again, you can relate this pretty closely to the other concepts, particularly mutual exclusivity. Typically, when we're trying to make up, say, survey responses, we want to have the different responses be exhaustive, but also mutually exclusive. So if they're mutually exclusive and exhaustive, then this thing is the exact same thing as the sum of the probabilities of all the AJ we saw before. And that's going to equal 1. Right, so if we have a set of mutually exclusive, collectively exhaustive events, then the probability that any one happens is equal to the sum of all the individual probabilities, which is equal to 1. So that can be very useful often. And we'll often see work deliberately try to create a set of such events to take advantage of these properties. That's pretty much it. So next we'll start talking about calculating probabilities. Thank you very much.